So here we are, come to help Chris get his truck running, and it's not running, and we broke down. So he's gone home to get a coil. Hopefully that's all it is, and we're running soon.
So I've got two coils. Now this one that says flamethrower on it, this is the original coil that was in the truck when I broke down. And it actually says flamethrower on it, and the flamethrower coil is what goes with the Petronix electronic ignition that I've got.
The best part about this system is it installs in the distributor in the location of the stock point.
So looking at the visual appearance of the coil, I can't see anything wrong with it. There's no bangs or dints in it. It's full of oil, I can hear that sloshing around, and it's not leaking any oil from it. So outward appearances look okay, there's nothing wrong with it. So when my truck broke down, I wasn't sure what was going on. And you know, we were trying putting fuel down the carb and looking for spark. There was a spark, but it was certainly a very weak spark, and I just so happened to put my hand on top of this coil, and I would say, well, I'm not going to say it was red hot, but it was probably above 50 degrees. You couldn't keep your hand on it comfortably, so it was pretty hot. So I thought, well, that's not right. So I went home. I went and got a spare coil out of the hoard. The car started up immediately and I drove home absolutely no problems. But a few days later I was just running the truck on the driveway while I looked at the radiator, and I noticed again, just touching the coil, that again it was getting red hot, and I was trying to understand why the coil would get hot. Now most likely it's something wrong with the Petronix ignition. Maybe it's actually turning the coil on for longer than it should be, but I don't know that. But I've also just been doing some reading around the subject of a hot ignition coil, and one of the things that has been suggested is that if you've got a large spark plug gap, or just if the HT gap is particularly large anywhere in the system, it can increase the primary current in the coil. Now I've got no idea whether that's true or not, but I just wanted to test that out and actually put it to bed. So this is a coil that led to all the problems, and this is a brand new coil. Now these aren't actually quite the same. This one has only got a resistance of 1.5 ohm. So this is definitely designed to run with either an electronic ignition or with a car that's got a ballast in it, which is basically just a big resistor. But this coil is it's a ballasted coil, in that it's got a higher resistance, and I think this one is 3 ohms. Well, I can't see anything written on it, but I think the resistance to this is 3 ohms, so we can try that. Now this coil has cooled down, maybe we could just give it a quick test. So just checking the resistance of my meter, what does it measure? It's about 0.5 ohms. I don't know if it's possible to null these out, these fluke meters. If you know how to null out a fluke 175, let me know. I don't know if it's possible or not, but it'd be nice if it read 0 on these test leads. So it's measuring 1.8 ohms, which if you add that to our 1.5, that's bang on. So nothing wrong with the resistance to the coil. Now of course, unfortunately, these coils are auto transformers, so it isn't like you can really easily test for a breakdown between the secondary and the primary, but I'm guessing that we should have quite a high resistance between secondary and primary here. And that's 6 kiloohms. Well, just for comparison, let's have a look at the new coil I bought, which is going to be slightly different. So let's see what the primary resistance is, which I'm going to guess in this is for 3 ohm coil. Okay, 3.5, so that's a 3 ohm coil. So let's just look at the resistance in the secondary winding now. 7k. So it's 1k higher than the flamethrower coil, but they're both in the ballpark. So I've got this little gadget here, and this is designed to try to give you an indication of how good the high voltage line is. So what you do is you take out a spark plug and you actually put it on the end of here, and then you clip this to some piece of grounded bodywork, and then there's a screw thread and there's kind of a graduated scale here. So basically you can open this up like this, and the spark has to jump further across the electrodes. And obviously you want the spark to jump as far as possible. The further it jumps, the higher voltage you've got. The high voltage connects to this end, and there's a little pointy electrode there and one here, and it's a screw thread. So I'm just opening it up at the moment, so the spark would have to jump further, and I'm closing it up, and the spark will jump less far. So basically what you do is you start off with a spark, and then you unscrew it like this until the spark stops, and that just gives you an idea of what your voltage is on your coming out from your coil. Now if you want to run a coil properly, of course we need to actually feed it with some pulse DC. In a car it's either going to be done by a set of contact points which open and close driven by some cam arrangement, or if you've got an electronic ignition it's going to be a high power transistor, or probably in more modern vehicles a MOSFET. But what I'm hoping to do is just use this relay here to replace a set of contact points. So I'm going to drive this relay from a signal generator, and it's a 10 amp relay, and I'm not expecting it to last that long, to be honest, but I'm hoping it's going to just last long enough to actually demonstrate this coil working, and maybe try to test both of them and see if we can maybe leave this one running and see if it gets hot. So I can see that this relay has actually got some wires on it, and it looks as though I actually configured it as like a multi-vibrator last time, so maybe I was playing with coils previously. This relay just came from the hoard, so I'm not sure what I was doing. But yeah, so let's go ahead and desolder these old wires off it and try and build a bit of test kit up. Now back in the day I actually used to build MOSFET drivers and stuff like that for actually running coils and you know, experimenting with them, but I don't really want to put the effort into doing that. I just want to do kind of a quick test, so I'm not going to do that today. Oh, I've just noticed the leg is melted on this. I think it's the coil on the relay, so I'm not going to poke about at that anymore because I think the leg will probably fall off if I do. And we may as well install it on a piece of Vera board that I've got to hand. God, how hard can it be to get the pins of a relay through a piece of Vera board? Obviously, quite hard. Oh dear, I'm being cack-handed today. Right, that'll do. I think I said earlier, I'm not exactly sure how long the contacts are going to survive on this relay, but I don't care. Got a tool somewhere for cutting these Vera board tracks, but I don't know what I've done with it. Okay, so those are the coil contacts as we thought. Let's just establish what's normally open and normally closed, etc. So I think this leg on the end must be the common. That's normally closed, so I'm going for that being the normally open. So if we go ahead and just connect these relay contacts, they're going to get hammered very, very quickly. So what we need to do is the same thing they do on an automotive distributor. We've got to actually fit a condenser. And if you're wondering what a condenser is, that's just an old name for a capacitor. So what we're going to do is we're going to fit a capacitor between the opening and closing contacts of the relay here. And what that's designed to do is to allow the well, it's designed to extinguish the arc between the contacts. So it means that the actual the coil will produce a higher output because you get a quicker rate of change. If you don't have the capacitor, what you get is you get a lot of arcing between the contacts of the relay, or your contacts of your points if you're installed on your car. So if you put a capacitor between them, the back EMF from the coil has a route back to ground, and it goes via the capacitor, so you don't get an arc, which means that the signal going to your coil, switching it on and off, is faster. That's my crap explanation, I'm sticking to it. Just scrounging through the hoard, I'm going to go ahead and fit this 220 nanofarad capacitor across our points contacts, and that's kind of an approximate value. The actual choice of this capacitor is quite important. One, you need kind of quite a high voltage rating, something above 400 volts if you were to actually use it in a real vehicle ignition. And the choice of capacitance value is very important. If you have too small a capacitance, then what will happen is it won't be effective, and you will generate an arc between the contact points, and that will burn the points out rather quickly. If you've got too big a capacitance value, it will slow the rate of change down across the coil, which will also reduce your voltage. So I'm going for a middle of the road. It might need fine tuning, but again, I'm just guessing it, so I'm going to put in a 220 nanofarad. So let's just bang that in. Ta-da! The other problem with using relays, though, is that the springs that return the contacts to the open position, they're not very strong, so they don't respond very quickly. So you can't run relays particularly quickly and they also have a habit of bouncing around. If you look at a set of points in a car, the actual contacts have got very powerful springs behind them, so they can open and close. Well, really, so they can close very quickly and they don't bounce. Well, unfortunately, that's not true with relays. So this one may just burn out immediately, but we'll have to see. So one of these wires is going to go to the negative side of the coil like that, and the other wire is going to go to the negative side of the power supply. And now all we've got to do is figure out a way of making this relay turn on and off very quickly. So before we set this relay up to vibrate, I'm actually just quite excited to see if our little relay driver works. So I'm just going to energize the coil on the relay, and hopefully we should get a spark jumping across those two electrodes. Fingers crossed, here we go. That looks quite good actually. Open our gap a bit. Wow, that's a hell of a gap. That's a good spark. It's actually almost a bit scary, that thing, isn't it? You know what, I'm kind of wishing that I'd built this using a MOSFET rather than a relay, because the problem with a relay is that it can't oscillate that quickly. It can't switch on and on very quickly. Because the amount of metal in it has a certain amount of mass and momentum, and yeah, you can't really beat it. I think looking at this relay, the data sheet for it kind of implied that it was, I think it said it was good for about up to 20 Hertz, or rather that was a maximum. So what I think we'll do is, I think we'll use a 555 timer. There's a few chips we could use to generate the oscillator. In fact, I was just going to plug it into a signal generator and use a transistor maybe to drive the relay, but I've decided to use a 555. Reason being, a 555 has good drive characteristics to be able to drive this relay and turn it on and off, and it has quite a wide supply voltage, so it'll work at 12 volts without needing any form of regulator or anything like that. So we're going to use a 555 timer because that's ubiquitous, and of course we're going to need a socket for when I burn out the 555 timer. Using an online calculator, I've worked out the resistor and the capacitor values that we need for our stable multivibrator. So we're going to... Oh, that was the capacitor that fell on the floor, wasn't it? No expense spares. It's a Nichicon capacitor. So yeah, top quality, no expense spared here. In fact, let's move that over a little bit. Might just interfere with my big chunky fingers getting the chip in, so let's move it over one. May as well go ahead and cut these tracks before I forget. So we're nearly there now. I'm just going to link pin 6 back to 2, and I'm going to do that very inelegantly because I don't really care. You know, I'm always amazed at how beautifully some people wire up Veraboard circuits. I'm always a little bit scruffy, I'm afraid. I'm never very neat at building these things, and I guess it's nice to take pride in your work, but I just can't be bothered. If I'm building something on Veraboard, it's a lash up. Anything I care about, I do a PCB for it. So yeah, I don't really bother making a lot of effort into doing these Veraboard designs. If wires cross over each other, so what, I don't care. So here's one I built earlier, well actually about 5 minutes ago. So I've gone ahead and I've finished this circuit. So we've installed our flyback diode across our relay coil just to protect the output transistor in the 555 timer, which we've also installed. And yeah, no build problems, it went together fairly smoothly. And I only had to sacrifice 2 555 timers in this, so I thought that was fairly good for me. Only destroyed 2 ICs. So all we need to do now is we need to connect it up to our coil and actually give this thing a go. So here are the two wires we're going to connect to the coil, but I haven't done it yet. But I've connected up the power, and hopefully you can hear that it's clicking away, and that's the sound of 20 Hertz. And I did check that on the oscilloscope, and well, I've got to admit 20 Hertz is actually a little bit slower than I imagined, so I might even recalculate the values for the 555 timer, and we may speed it up a bit, because I think this relay will go a bit quicker than the rate at which we're running it. Hopefully that should work. Let's give it a try. Oh, Jesus. Yeah, don't adjust that with the coil running. Well, Christ on a bike, I just got a right belt off this coil, and did anybody spot my mistake? What it was is I didn't have this ground strap attached, which you need to do. You need to have this circuit completed. So my high voltage jumped across to here, and because it couldn't go to ground because I didn't have this wire clipped on, which should have been clipped on like that somewhere, it actually chose to jump over this piece of plastic and into my body, and then probably capacitively coupled back through the ground and the surroundings into my arm, and yes, that really bloody hurt. I'm going to turn this off this time. Don't think I'm going to touch that thing again. Hopefully you could see there, not only were we getting the discharge across the spark gap, we're also getting some secondary discharge between the top of the coil and the ground terminal, so it was obviously flashing over here when this gap got too wide. Don't really want that, because I'm concerned that some of those nasty voltage transients can get back into my power supply system, which would be bad. I think I might just temporarily bodge in a couple of largish value capacitors here. About the largest I've got to hand, and just going to use these to offer a little bit of smoothing and help to kill any transients that might try to get back to the power supply. We might even find that adding these capacitors has made the whole spark a little bit more potent, because we're not getting the voltage drop now in the wiring up to the power supply. These wires I've got to my power supply, they're quite long. And I actually think that has had an effect. Of course, making sparks and getting electric shocks is great fun, but the whole idea of building this little circuit board is, what I wanted to find out is, does the spark gap length have an effect on the primary current being supplied to the coil? And so we need to answer that question. So unfortunately we don't appear to get a meaningful reading out of this current meter on my power supply because of the nature of the pulse current. So you can see there, it really can't make up its mind what it's actually reading. So what I think we need is an old school analog meter, so let me find one. So I think the current on these Avos goes up to 10 amps. I'm not sure though, just got to double check that. Yep, DC range 10 amps. Well, I'm not going to claim the actual accuracy of the DC current reading. I mean, let's face it, somewhat open to interpretation because it's going to be pulse DC anyway. But the advantage of using a meter like this, it's an old Avo and it's built like a proverbial brick privy, and they have a huge amount of damping on the meter movement, which is good if you've got a lot of pulse currents and stuff like that. It's nice to have that amount of damping on the meter, because it means that rather than the meter movement, the needle twitching around or floating up and down like it does on a digital reading, you will get the needle should find a centre position. So I'm just going to put that on now, and we're going to take a current measurement. I'm going to wind in the spark gap, so we're going to go for a very, very short spark length now. Well, I say short, yeah, that is pretty short, so let's try that. and the reading is 2 amps. I'm just having to hold the meter in shot there, so it's not very good. 2 amps. And now I'm going to open up the spark gap. So that's very wide now. And we will apply the power again. And that appears to be slightly under 2 amps. Maybe I went a bit too far there. Okay, that was slightly under 2 amps. I'm going to close it right back up. And about 2 amps. I'll be the first one to admit that this experiment is a little bit crude, of course, but it does appear from what I can tell that there isn't really any major difference between the on the primary current if we have a very short spark gap like this, or if we're jumping a very long gap. It appears that the amount of current we supply to the coil is the same. And the reason I wanted to find this out is I was trying to explain why the coils were actually overheating. Now, it's more than likely that it's just a problem with either the coil or my set of electronic points I've got in the car. Maybe there's a problem with the dwell and it's actually switching the coil on for longer than it should. But I just wanted to prove that because a few people had said, well, if you've got your spark plug gap set too wide, it draws more current from the coil. Well, I think we've disproved that. Your spark plug gap doesn't really have any meaningful effect on the amount of current that you pull. So what I'm going to do next, I'm going to swap out this brand new coil for this one that appeared to fail in the car and see if there's any difference. So I've got the points gap here set to, well, I don't know what it's set to. Shall we try and measure it? Let's see if I can measure that. That might be interesting. Okay, bang on 7mm. So before I swap this coil out, let's just remind ourselves of what the arc intensity and looks and sounds like, and again just double check the current reading. So here we go. So we're drawing just under 2 amps and quite a vicious spark and quite a loud crack associated with it. Let's get our positive and negative right. That's positive on that side. Okay, let's power it back on. And we're getting no spark at all now, and the coil is actually drawing more current. The coil's actually drawing 3.5 amps. Now that kind of might be expected because this coil is it's got a lower internal resistance. It's meant to be 0.6 ohms rather than 3 ohms, so it should actually be drawing more current anyway, but we've got no spark. So I'm going to go ahead now and I'm going to close up our spark gap. I'm going to turn it off first, so I'm sure I only got a belt because I didn't have an earth lead on it, but I'm not taking the risk. So again we're drawing 3 amps. So I've actually closed up our spark gap to 0 now, so the two electrodes are touching each other, but that's no good, so I'm going to put a bit of a gap in. I'll just wind it back, just a little bit of a gap there. And apply the power. Oh, and you can see there is the most feeble looking spark on the planet. So this coil is not really working. I can only guess that somehow it's breaking down internally. I can't say more than that, but obviously it isn't working. Let's open that gap up a little bit more. And again, it stopped working. I don't know if I'll be able to measure that gap. It's actually probably too small. Let's try. So it looks like our spark gap now is about the thickness of this stick. And this stick is 2mm. So we've got a spark gap now set of about 2mm. Based on our little bit of testing here, it would appear that this black old coil that we removed off the truck after it broke down, it does occasionally produce a spark, but it's certainly very feeble in nature, and it isn't even able to maintain jumping the gap of about 2 millimeters. Now I think typically they say that a voltage will jump. I think they say it's about 1 millimeter per 1000 volts. It depends on things like atmospheric pressure and moisture, but I'm talking typically. So this one is barely making 2000 volts because it's only periodically jumping across the gap. And just for one final time, let's just put the new coil in. Right, I think that's enough of that. Jesus Christ on a bike, I just got a right belt off this coil.